Hello student, welcome back to the course on optimization methods for civil engineering. So, in the last class we have discussed few line search techniques. So, I am calling it line search because we are trying to find out an optimal solution of a single variable function. So, in the last class we have discussed mainly region elimination technique. So, we discussed the interval halving method, we discussed the golden section search method, then also we discussed the bisection method. Okay. So, before that we discussed the bracketing method. The first step is to bracket the optima, and after that we are applying the region elimination technique for finding the exact optimal solution of the problem. So, today I will discuss another algorithm for finding optimal solution of a single variable optimization function. So, I hope all of you know Newton-Raphson method. So, this method is applied or this method is used to find the root or roots of the function. Okay. So, I can find out the root of this function, that is f of x equal to 0. So, I have to find out the value of x, and that is the root of this particular function. So, I can apply Newton-Raphson method for finding the root. Okay. Suppose if I take an initial point, we call it x n, and this value is f of x n. Okay. So, this value is f of x n, and then if I approximate or if I approximate the gradient at that point. So, I can calculate the gradient, that is the first derivative gradient, which is f of x n minus f of x n plus 1. So, this is the line, the tangent is touching the x axis at x n plus 1. So, f of x n minus f of x n plus 1 divided by this distance. Okay. So, divided by this distance. So, what is this? This is x n minus x n plus 1. So, from this triangle I can find out the derivative. So, derivative is these values. Okay. So, this value, what is this? This is f of here it is f of x n, and here it is f of x n plus 1. Okay. So, this is this value is f of x n plus 1. Okay. So, now f of x n plus 1 is equal to 0, and if I put f of x n plus 1 equal to 0 in this equation. So, and then if I rearrange the terms. So, I am getting x of n plus 1, which is equal to x n minus f of x n divided by the first derivative at x n. So, what I am getting, that using this equation I can approximate that x n plus 1. Okay. But x n plus 1 is not the root of this particular function. So, here I am getting the value of x n plus 1. So, I can check whether f of x n plus 1 is, what is this value. So, if this value is not 0 or near to 0, that means that is not the root of this equation. Then what I will do? I will calculate the next value, that is x n plus 2. So, I will draw a tangent, and this is the value of x n plus 2. So, x n plus 2 equal to x n plus 1 minus f of x n plus 1 divided by derivative at x n plus 1. So, and that way I can find out x n plus 3, n plus 4, something like that, and every step I will check whether that function value is 0 or not, or if it is near to 0, then I can terminate this iteration. So, this is an iterative based process. So, next step is I will calculate x n plus 2, okay. Then I will calculate x n plus 3, and then I will continue, and every step I will check whether x n plus 2, okay. So it is 0 or not basically. So or what I can do that it should be equal to 0, but it will never be 0 here. So what I can do, I can take that the function value, okay, that absolute value of x n plus 2 or whatever. So this should be less than equal to, this should be less than equal to some epsilon, okay. So some epsilon value. So I will terminate my iteration once that f of, okay, x n plus 1 or n plus 2 or is basically less than equal to some epsilon value. So epsilon value maybe you can put it as a precision, suppose 10 to the power minus 3 or 10 to the power minus 6 or 10 to the power minus 12. So as per your desired precision, so you can put the epsilon value, and I can terminate this iteration. So once the function value, absolute value of this particular function is less than that precision, okay. So that means that is the acceptable error, epsilon is the acceptable error. So once the function value is less than acceptable error, so in that case I can terminate my iteration. So this is your Newton-Raphson method for finding the root of a function, okay. Now I can apply the same technique for finding the optimal solution of a function, okay. So how we can do that? So in case of optimization problem, the first derivative should be equal to 0. In case of root finding problem, the function value is 0. Root finding problem, that function value is equal to 0, but in this case the first derivative is equal to 0. So if we consider capital F x, which is equal to the first derivative of the original function small f x, okay. So if I consider capital F x, which is equal to the first derivative of the original function. So therefore in this case the capital F x, so capital F x should be equal to 0. That means what we are doing, we are trying to find out root of this particular function, root of this capital F x function. So therefore I can apply the same Newton-Raphson method for finding the root of this capital F x function, and which is, suppose I can apply that f x n plus 1, which is equal to x n. Now that function value at x n and the derivative at x n, derivative means derivative of not the original function, but derivative of the derivative of capital F x. Now if I put that f x n is nothing but the derivative of the original function, and if I take derivative of the capital F x function, so that will be the second derivative of the original function. So therefore I can write this particular your equation. So this is an iterative based equation, that means I can find out x n plus 1, which is equal to x n. So this is, we will start with x n, that means suppose we will start with x equal to 0, okay, and x n minus first derivative at x n divided by second derivative at x n. So I am getting this equation. So this is your Newton-Raphson method, and I can find out the root of the capital F x function, and that will be the optimal solution of the original function. Okay. So now this is your capital F x, and this is the starting point, and I will approximate what is x n plus 1, and then I will approximate what is x n plus 2. Then after some iteration I will get the root of capital F x, and that root of capital F x, that means I will get the solution that capital F x equal to 0, and that means the first derivative is equal to 0, and whatever solution you are getting, so that will be the stationary point. Okay. So that will be a stationary point. Okay. So I can apply this Newton-Raphson method also for finding the optimal solution of a single variable function. Now question is that whether you will apply the region elimination technique or you will apply this Newton-Raphson method. Okay. So, if you compare with region elimination technique, in the region elimination technique we are not calculating the derivatives. Okay. So, derivative calculation is not there, we do not we did not calculate it. So, what we are doing there, we are just calculating the objective function value. Okay. So, in the case of region elimination technique, so we only calculate the function value, but here in this method you have to calculate the derivative. Okay. Now, question is that if you are working with a simple function, then derivative in the program itself you can give the derivative of that particular function, but when you are working in a very complex function, derivative calculation is not that easy, then it will be difficult for applying Newton-Raphson method. Another issue is that I can calculate the derivative, okay, using numerical method. Okay. So, I can calculate the derivative using numerical method. I can apply the forward differentiation technique, the backward differentiation technique or central differentiation technique. Okay. Now, if you are applying the forward differentiation, so what is that? Suppose I can calculate the derivative of the function. So, derivative of this particular function, which is equal to, I can calculate that f of x plus delta x minus f x, okay, minus f x divided by delta x. So, this is the forward differentiation. So, I can apply, and here I can calculate the derivative using numerical technique. So, in that case, using this equation I can calculate. So, here what you need basically, so you need two function evaluation for calculating the derivative. Okay. Similarly, you can calculate the second derivative also numerically, but you need more number of function evaluation. Okay. Therefore, if you compare with the region elimination technique, so you have to compare that with that how much function evaluation you need basically to reach the optimal solution. Okay. So, therefore, depending upon the situation, we can choose one of the technique, okay, either region elimination technique, interval halving technique, golden section. As you have seen, the golden section method is more efficient than the interval halving method. So, you can go for golden section method, you can also apply the bisection method. Okay. Now, let us see some example problem. So, what I will do basically, so I will solve a single example problem using different techniques. So, just to demonstrate how these algorithms are working. Let us take this particular function. The function is f of x equal to x cube minus twice x square minus 10 x minus 10. So, this is a very simple function and I can plot it. So, if I plot it, so this is the plot of this particular function, and by looking at the plot you can guess that there are two optimal solution between minus 3 and plus plus 5. Okay. So, one solution is somewhere here. So, this is one solution and another solution is somewhere here. So, this is another solution, and by looking at the curve itself, so you can tell that this is the minimum. Okay. So, this is the minimum of this function and this is the maximum. Okay. So, maximum of this particular function. Now, if I say that the source space is between minus 3 and plus 5, so in that case this is not a unimodal function. Okay. So, there are more than one optimal solution, but if I take, suppose if I take only this portion, okay, so only this portion, that means from 1 or 0.5 to 5. So, if you consider that this particular function between your 1 and 5, so that is a unimodal function. Okay. And similarly, if I say that this particular function between 0 and minus 3, that is also a unimodal function. So, as you have said that whatever method we have discussed, okay, so this is for a unimodal function, that means there is only one optimal solution. Okay. So, I can apply the necessary condition. Okay. So, first derivative is this. Okay. So, this is the first derivative and I can apply necessary condition for optimality, that means that first derivative should be equal to 0, and if I put it equal to 0 and if I solve, and then I am getting x star equal to 2.6103 and that is the minima somewhere here, and another solution is minus 1.277 and that is the maxima of this function, and I can apply the sufficient condition. Okay. Sufficient condition means I can take the second derivative. Okay. So, I have to check whether second derivative is 0 or non-zero. If it is not 0, then I have to look at the derivative value, second derivative value. If second derivative is positive, so in that case this particular point is a minima, and if second derivative is negative, that particular point will be maxima. Okay. So, I can apply the necessary and sufficient condition and to find out the optimal solutions. The first step, you are getting the stationary points, and after that you can apply the sufficient condition to check whether that stationary points are a minimum point or a maximum point or an inflection point. So, I can do that, but in this particular example we will try to apply the region elimination technique as well as Newton-Raphson method for finding the optimal solution of this single variable function. Okay. So, let us solve this problem. The first one is interval halving method. Okay. So, as we have explained the interval halving method. So, what we are doing, we are taking 3 points and we are dividing this region in 4 equal parts, that means 25, 25, 25, 25. Okay. So, therefore, x m is the mid and then x 1 is between a and x m at the midpoint, and again x 2 is the midpoint between x m and b. Okay. So, one of these condition will be true. So, what after taking these 3 points, so one of these, so this is condition 1, this is condition 2 and this is condition 3. That means, f of x 1 is less than f of x m. So, f of x 1, that means in this case anyway this figure is not showing that first condition, but so if the first condition is true, that means f of x 1 is less than f of x m, then you will eliminate the region x m b. So, in that case what will happen, that a equal to a, so a will not change, but b will be equal to x m. Okay. So, in that case b will be equal to x m. Now, in case of this one, that means in case of the condition 2, if condition 2 is true, that means if f of x 2 is less than f of x m, then what you will do, you will eliminate a x m. That means, this from a to x m you will eliminate. So, in that case a will be equal to x m and b will be equal to b, b will unchanged. Now, if the third condition is true, that means if f of x m is less than f of x 1 as well as f of x m is also less than x 2, f of x 2. So, in that case the region a x 1 and x 2 b. So, in that case a will be equal to x 1 and b will be equal to x 2. So, what will happen? So, if you take these 3 points, so one of these 3 conditions will be true. So, accordingly, so you will change your upper bound and lower bound. Okay. So, let us apply. So, in this case, as I said that I have taken this function between 0 and 5, that means lower bound is 0, upper bound is 5, and within that region this particular function is a unimodal function. And so, if condition 1 is true, so in that case a equal to a and b equal to x m. If condition 2 is true, then a equal to x m, b equal to b, and if condition 3 is true, then a equal to x 1 and b equal to x 2. Okay. Now, let us start this algorithm. So, first iteration. So, this is iteration 1. Okay. So, this is iteration 1. then lower bound is 0, upper bound is 5, then I have calculated the midpoint, that is 2.5. So, what is xm? Xm is 0 plus 5. So, I am calculating xm 0 plus 5 divided by 2. So, therefore, it is 2.5. Similarly, I have calculated x1 and x2. Okay. Now, you calculate the function value at x1, xm and x2. Now, you check which condition is true. So, in this case, the condition 3 is true, that means f of xm is less than f of x1 and as well as f of xm is also less than f of x2. So, in that case, what will happen? A equal to x1 and b equal to x2. So, I have revised that one, that A equal to x1. So, you just see this x1 value has come to as an A, and b equal to x2. So, b is also coming like this. Okay. So, b equal to x2, and I calculated what is a minus b just to check when we have to stop the iteration, and then the optimal value in this. So, it is coming 2.5, that is a minus b by 2. Okay. Now, I am getting new a and b, that is now in the second iteration, the a equal to 1.25 and b equal to 3.75. Then I have calculated what is x1, then xm, x and x2. Okay. And then you calculate the function value, and in this case again the condition 3 is true. So, therefore, that a equal to x1. Okay. So, x1 is coming as a and b equal to x2. Okay. So, now again you calculate what is a minus b, absolute value of a minus b, and the optimal solution. So, in that case it is 2.5, 2.5, and now in the third iteration again you calculate what is x1, xm, x2, then you calculate the function value and just see which condition is true. In this case also the third condition is true, and accordingly you sense what is the new a and b value. Again you calculate x1, xm and x2, and you also calculate the function value, and in this case the second condition is true. Okay. The condition 2 is true. So, second condition is true means a equal to xm. Okay. So, therefore, in the next iteration a equal to xm. So, this is coming as a xm, and b will not change. So, b is 2.81. Then again you calculate your x1, xm, x2, you calculate the function value. Now, you just see this condition 1 is true. Okay. Condition 1 is true. 1 is true means a equal to a. So, therefore, a is not changing in this iteration, and b equal to your xm. So, this xm is coming as a b here. Then you again calculate x1, xm, x2. Then you just continue this iteration, and every iteration you just check what is absolute value of a minus v. Once it is reaching the precision, you can stop your iteration. Suppose this is coming here, this is suppose this value is less than 0.01. If I put 0.01 is the precision, so you can stop there. Okay. So, even you can stop here itself. So, you can, if you are taking 0.01 as your precision, and then the optimal solution is coming 2.6104. So, as you have seen, the optimal solution in that particular region is 2.6103, and you are getting 2.6104. Okay. So, if you are doing it for another 2-3 iteration, then you will get 2.6103. Okay. So, you can stop your iteration. So, this method is interval halving method. So, now I would like to discuss one point here. So, if you look at that the first iteration, how many function evaluation you are doing? 1, 2, 3 function evaluations at the first iteration, and after that you are doing 2 function evaluation. That means, if I calculate function evaluation, here it is 3, then 2, something like that. So, you can see that if you are doing it for up to 11, okay. So, 11 into 2, that means 10 into 2, that means 20 plus 3, that means up to this step you have done 23 function evaluation, okay, 23 function evaluation. So, as I have said that efficiency of the algorithm can be compared by using the number of function evaluation you are doing. So, in this case if your iteration is up to 11, so that means 23 function evaluation you have done here. Okay. So, but anyway, so we got the solution 2.610 or 04. Now, let us see the next example, next method. So, next method is the golden section search method. So, in this case what we are doing, we are taking 2 points, that is your x 1 and x 2, and x 1, what is x 1? X 1 is a plus tau. So, tau is 0.618 okay, L. Okay. So, L is the absolute value of A minus V, and similarly I am taking another point x 2. Okay. So, x 2 is B minus 0.618 L. Okay. So, you are taking 2 points here. In case of interval halving, so you have taken 3 points, but here you are taking 2 points. Okay. And then you will apply the region elimination concept. So, in that case you will compare the function value between x 1 and x 2. So, the first condition is if f of x 1 is greater than f of x 2, that means f of x 1 is greater than f of x 2. So, in that case what will happen? The region x 1 to B will be eliminated. Therefore, A will not change. So, A will be equal to A, then B will be equal to x 1, because this particular region will be eliminated. Okay. So, if this condition is true, now if the next condition is true, that means if it is not true, then second condition is f of x 2 is greater than f of x 1. That means the function value at x 2 is greater than the function value at x 1. So, in that case what will happen? This particular region will be eliminated, okay, and therefore, A equal to x 2 and B equal to B. So, B will be unchanged, but A will change to x 2. Okay. So, in this case we are just applying these two conditions. One of these conditions will be true. Okay. So, let us go to the table. Here also we have started from 0, that A is 0 and B is equal to 5, okay, between 0 and 5. Then I have calculated what is the value of x 1. So, x 1 is that A plus 0.618 L, and similarly I am also calculating the value of x 2. Okay. Now, you calculate the function value at x 1 and function value at x 2. Now, in this case that f of x 2 is greater than f of x 1. Okay. So, that means this is the second condition, is not it? This is the second condition, that is f of x 2 is greater than f of x 1. Then what you will do? You will change A equal to x 2 and B equal to B. Okay. So, A will be equal to x 2. Okay. So, this x 2 is coming here. Okay. So, this x 2 is coming here and B will not change. Then you calculate what is nu x 1 and nu x 2, and you are calculating the function value, and in this case the first condition is true. What is the first condition? First condition is f of x 1 is greater than f of x 2. So, in that case A equal to A and B equal to x 1. So, A will not change now, A equal to A, but B will be equal to x 1. Okay. Then you are calculating again nu x 1 and x 2, and as I have said that one point will be the previous point, either it will be x 1 and x 2. So, you can see that these 2 points are same, and similarly these 2 points are also same. So, that means in every iteration you are doing only one function evaluation, because one point will be a point which you have got in the earlier iteration. Okay. So, in this case that f of x 1 is greater than f of x 2. So, accordingly you will change your upper bound and lower bound, and you just see if you just go this is iteration 3, 4, then 5, 6, something like that. So, I have done it up to 20th iteration, and you can see that the error is decreasing. Okay, distance between a minus v, okay, distance between a and b is decreasing, and once it is reaching the your that desired precision, okay, so you can terminate. So, I have done it up to 20 iteration, and you can see the you have a very narrowed region, and that distance between a and b is 0.00053. Okay. And you are getting the solution, and that solution is 2.61033403. Okay. So, you got the solution using golden section search method. Now, if you compare the function value, how much function value you have calculated, okay, calculation of function value, you just see that in the first iteration I am doing 2, and then every iteration I am just calculating one function, I am doing just one function evaluation. That means, if you go up to 11, then how many function evaluation you have done? You can see that function evaluation is, that means 10 plus 2, that means 12 function evaluation you have. Okay. But in case of interval halving method, so you have done 23 function evaluation. Okay. So, anyway, so you did not get the solution as compared to the golden section search method in 11th iteration, but I think you got the solution somewhere here. Okay. So, somewhere here you got the solution somewhere in 13th iteration. Okay. So, that is 0.009. So, that is your less than 0.01. Okay. So, that way you can compare the algorithms. I hope this is clear to you. Then let us go to the next algorithm. So, next algorithm is the bisection method. So, in bisection method, so what we are doing? We are taking a point z. Okay. So, z, and which is a plus b by 2, that means at the midpoint. Okay. So, at the midpoint we are taking this point z, and then we are just checking whether the derivative value at that particular point is less than 0 or greater than 0. If it is less than 0, then we are eliminating the region A z. Okay. So, A z, and if it is greater than 0, then we are eliminating the region Z b. So, if condition 1 is true, okay, so this is condition 1 and this is condition true. Now, if 1 is true, so in that case what will happen? That means the derivative at z is less than 0, that means we are eliminating a z. So, in that case a will be equal to z, okay, and b will unchange, b will be equal to b. Now, if the second condition is true, so in that case we are eliminating z b, that means a will unchange, in that case a equal to a and b equal to z. Okay. So, we will just apply these two conditions, and if we do it for some iterations, and you will get the optimal solution of this particular functions. Okay. So, let us apply this bisection method. So, here again we have started from with 0 and 5, that means a equal to 0, b equal to 5, and this is x m. So, this is nothing but z, z is at the midpoint. Okay. So, z equal to 2.5. So, I am getting this z value, and now you calculate the f z value. Okay. So, this is your f z. Okay. So, f z or x m. Now, you just see whether it is negative or positive, whether it is less than 0 or greater than 0. If it is less than 0, that means the condition 1, that means a equal to z and b equal to b. Okay. So, in that case what will happen, that A will be, because it is a negative, the first condition is true. So, therefore, A equal to Z. So, A equal to Z means Z here is 2.5. So, this value is coming here, okay, A equal to Z, and B will unchanged. Then you calculate new value of Z, calculate, sorry, this is the derivative value, not your function value. So, the derivative is now 17.18 and that is positive now. So, if it is positive, what will happen? If it is positive, A will not change, B will be equal to Z. Okay. So, A is not changing and B is equal to Z now, okay. B is equal to Z, and then you calculate new value of Z, new derivative value, and in this case positive. So, positive means that A is not changing, B is equal to Z, and then you continue your iteration. Okay. So, you can see that you are getting, suppose you are getting here, I have done up to 20 iteration, and 20 iteration you are getting A minus B, absolute value of A minus B is 9.5367 into 10 to the power minus 6, and the solution is 2.6103. Okay. So, anyway, so we have some more decimals here, but solution is 2.6103. Okay. So, we got the solution. So, you can compare that in terms of efficiency with the reason elimination technique. Now, here suppose if I calculate the derivative numerically, numerical calculation means at every iteration you have to do two function evaluation. Okay. So, to calculate the derivative, suppose if I calculate this derivative numerically, maybe using forward differentiation or backward differentiation. So, in that case I have to do two function evaluation. So, that means every iteration. So, I am doing two function evaluation. So, if you are comparing with up to 11th iteration, so we are doing 22 function evaluation. So, at 11th iteration, so we are getting the A minus B value, absolute value of A minus B value is 0.00488 and the solution is 2.6098. Okay. So, that way I can compare, and anyway, so if you do some more iterations, you are getting the optimal solution of this particular problem. Your just error is decreasing. Okay. So, in this case it is up to 10 to the power minus 6. So, I can also apply this bisection method for finding the optimal solution of a single variable function. So, as I have mentioned earlier, so in that case you have to calculate the derivative of the function, and many times we are not calculating the derivative because derivative calculation is not that easy for some your problem. Okay. So, therefore, if the derivative calculation is not that difficult, so in that case this is one of the efficient method. Okay. So, and if you can put the derivative value directly in the iteration, then this method is quite efficient. Okay. So, this is another method. Then let us check the Newton-Raphson method. So, I can also, as I said, that I can also apply the Newton-Raphson method for finding the solution. Okay. So, in this case what you have to do to apply Newton-Raphson method. So, I need the first derivative as well as second derivative. Okay. Now, for this particular function, so I can calculate the first derivative. So, first derivative is 3x square minus 4x minus 10, and similarly I can calculate the second derivative, or that is 6x minus 4. So, in this case directly I can put the derivative here. I can write the equation something like that, that x n plus 1, which is equal to x n, okay, minus the first derivative is 3 x square minus 4 x minus 10, and the second derivative is 6 x minus 4. Okay. So, I can apply this particular equation iteratively for finding the optimal solution of this particular function. Okay. So, let us start with x naught equal to 1. So, in this case we have to start our algorithm from a starting point. So, let us take x naught equal to 1. Okay. Now, x, this is the first point, and then the derivative here is minus 11 and the second derivative is 2, and if I apply this particular equation, then x n plus 1 I am getting 6.5. Now, this 6.5 I will put it here. Okay. So, I am calculating the second approximated value. So, in that case at 6.5, the first derivative is 90.75, the second derivative is 35, and then x n plus 1. Okay. So, that means I am getting 3.9071. Now, I am doing the third approximation, I am getting 2.8698, then the fourth one I am getting 2.6256, then the fifth one I am getting 2.6104, and sixth one I am getting 2.6103, and you can see that the derivative value is decreasing. Okay. So, at optimal solution the first derivative will be equal to, first derivative should be equal to 0. So, in this case it will never be 0, but it will be near to 0. Okay. So, we are getting suppose if we stop our iteration at 7th iteration. So, 7th iteration I am getting is 2.6103, and the derivative value at that particular point is 1 to the power minus 8. Okay. So, that means it is near 0, and at optimal your point the derivative should be equal to 0. So, I am getting the solution. Now, if you look at, if you compare with the region elimination technique, you just see with a few iteration I am getting a very quality solution. Okay. So, with only 7th iteration I am getting optimal solution almost, and the precision is 1 to the power minus 8. But question is that computational complexity can be calculated, that how much function evaluation you are doing. That means, at every your first derivative. So, you are calculating, you need 2 function evaluation, and for the second derivative you need additional 1. That means, every iteration you are doing 3 function evaluations. Okay. So, that way computational complexity of this problem may be more than the golden section search method, will be more than golden section search method. But as I said, that if you can directly, suppose for this function I am not calculating the derivative in every iteration. So, what I am doing, I am giving the derivative value directly. So, in that case this algorithm is quite efficient if you can put that one, suppose in your optimization problem. So, you have a very decent function and you can actually code the derivative value in your program. So, in that case the Newton-Raphson method is quite efficient. Okay. So, it will be more, but if you need to calculate the derivative using numerical method, so in that case it may not be that efficient. Okay. So, in that case you can apply the golden section search method instead of Newton-Raphson method. But if you can calculate the derivative directly from the function the way I have done here. So, in that case in a very few iteration you will get your optimal solution. Okay. So, in this case as you have seen that in the 7th iteration I am getting the optimal solution of this problem with an accuracy level of 1 to the power minus 8. If I take another starting point. So, as you have seen that this particular function has 2 optimal solution. Okay. This part has 2 optimal solution. If I start with x naught equal to 0, so you just see, so I am getting a different optimal solution. Okay. So, that is on the other side, that is minus 1.277. So, that is the solution I am getting in 7th iteration. So, therefore, in Newton-Raphson method, so we are not specifying the lower bound and upper bound, but we are starting with a single initial solution. So, from the that is we call it starting point, and depending upon the starting point, if you have a unimodal function you need not worry. So, you will get that particular solution only, but if your problem has more than one optimal solution, depending upon what initial solution you have chosen, so you will get one of them basically. Okay. So, in this particular class, so we have discussed Newton-Raphson's method for finding the optimal solution of a single variable function, and then we have solved this example problem using region elimination technique, that is interval halving method, the golden section source method, then bisection method, and also solve the problem using Newton-Raphson method. Okay. Thank you.